Yes?
Does that mean that salt Ag can be oxidant and reductant depending on like the number between?
I'm saying that the number refers to that reaction. And so in this reaction, we would call this the oxidant. Yeah? Because it's the thing that gains electrons. But what I'm alluding to is the fact that in reality, we can think about it like this, because sometimes, in fact, the reaction will go this way. It all depends on what else it's reacting with. Yeah? And we're going to look, when we start looking at galvanic cells after morning tea, this will hopefully become a bit more clear. Sir?
So if you were to put it the other way, it would change your E standard value?
Can someone, well, I won't. Let us all together in our minds slap this man, because he said the most evil thing possible. You must never change the sign on the number. Were you taught to do this at school? No. Was anyone taught to do this at school? Really? They said you can change the sign on that if you turn it around? Really? Must never change the sign on that number. E standard is plus 0.85 volts, the end. It's never negative 0.85, never. People teach, maybe people are too shy to say now that I'm getting so excited. Every year I will come across the occasional few students who have been taught at school that you can change the sign. And it's just such a bad, wrong thing to do. It's one of those things you can do in the very small box that is high school chemistry. And it works so long as you then fiddle some other things as well. And teachers go, oh, well, it's helpful because it's easier to get the answer. But it's just wrong. Right? So you never change the sign. Never change the sign. Sorry, I'm harassing you now. Never change the sign. Yeah? But thank you for saying it, because I would have forgotten, and now I get the chance to say, never change the sign. Right? Sir?
Can you change the sign on it?
Thank you for asking. No. No. So this number refers to this reaction. There is no such thing as an oxidation potential. This is one reason why I don't like this idea about calling it an electrode potential. There's all sorts of good reasons why they can say, oh, well, it's better than reduction potential. But if you call it the reduction potential, then you know what you're talking about. It refers to this sort of reaction, where something is being reduced. Whereas if you say it's an electrode potential, then you don't necessarily know. And it also seems to me that an electrode potential potentially could refer to a reaction that has to have an electrode in it. And that, of course, is not true either. These apply to any sort of redox reactions. So I'm going to keep saying reduction potential. When you come back and see me in first semester, I may have changed my tune by then, but we'll see. Right. And then we've already talked about that endlessly. That little thing together, the Ag plus with a line and then Ag, that little bit together is called the redox couple. And the redox couple is always written with the oxidant and then the other thing in that order. So that could be Fe3 plus, Fe2 plus. It could be I minus and I2. It could be copper, 2 plus and copper. It could be silver plus and silver. Always that order of reactant and product when you write it as a reduction reaction. Yeah? Okay. The We0, what does it mean if we say E standard? E standard tells us that all the species, ions, molecules, etc., in the reaction in question are at standard conditions. Which means that if you have something dissolved in water, then its concentration is 1 mole per litre. And if you have a gas, like that NO2 gas we had in our copper one, then that gas needs to be at 1 atmosphere pressure. And these are going to be the only options for us for bridging chemistry, because they're the only options for us at school. In 191, we're going to move on and see how you deal with it when the concentrations aren't 1 mole per litre. But for the moment, we're going to keep everything nice and straightforward. So the concentrations will always be 1 mole per litre, and the gases, where very occasionally we would see gases, are at atmospheric pressure. Okay? So standard conditions are a little bit different to standard states that we talked about last week. And then just finally it says E-standard values are obtained by experiment. Okay? It's like enthalpies of formation. You can use them for doing stuff, but at some point someone had to work out what they were to put them in the book. And so you can work all these out by doing experiments, and that's what we're going to talk about after the break. Right? How those experiments work to get you these numbers. Okay, so what we then... I think what I want to do now, until we get to biscuits, is, again, rip to pieces another one of those things that everybody has drilled into them at school. Right? Not because it's wrong, but because you don't have to always do it that way. So let's go back now to our copper and nitric acid reaction. Here are the numbers, right, which you can look up in a book. So E standard for H plus and NO3 going to NO2 for that redox couple is plus 0.80 volts. And then if you look up the one for the copper, E standard for copper 2 plus copper, that is plus 0.34 volts. And what we can do is this. We can just look at those two numbers and we can recognize hopefully that the one for the nitric acid is the more positive number. Right? It's a bigger number. That means that if we compare the oxidants in each of our two redox couples, the H plus and the NO3 minus here, and the copper 2 plus here, we can say that H plus and NO3 minus is the best oxidant because it's got the bigger number. A solution of H plus and NO3 minus wants to get electrons for itself more than a solution of copper 2 plus ions does. Right? These are inherent desires of the chemical species, if you like. Right? So this number tells you that this is the best oxidant. This wants electrons more than this does. What I want to do, this isn't on here, but I'm going to do this on the board. There are, and I'm not going to balance these because I can't be bothered, but there's two possible reactions you could do here, right? Remember that a redox reaction involves a reduction and an oxidation. So let's imagine for these two redox couples that there's going to be two possible redox reactions that you could do, right? You could have the case where the top one is the reduction and the bottom one is the oxidation. Yeah? So this would look like this. It'll be H plus and NO3 minus, and copper gives copper 2 plus and NO2 and water. Okay, this is not balanced. Right? So that would be the case if the top one was the reduction and the second one was the oxidation. The option would be to be the other way around, that the top one was the oxidation and the bottom one was the reduction. If that was the case, then it would be this. It would be copper 2 plus NO2 plus H2O gives copper and H plus and NO3 minus. Okay, are we happy with what I've done there? For each of those two redox couples, you can either have it written, you can either be one way or the other way. So the top one is what you would have if this was the reduction in your redox reaction, and so the oxidation had to come from this one, and the oxidation would be copper going to copper 2 plus. Yeah? This number refers to a reduction, but just not worry about that for the moment. For these two redox couples, we could have this turning into this, that would be a reduction, and so in a redox reaction, you would have to have copper going to copper 2 plus. That would have to be the oxidation that goes with this reduction. Does that make sense? Yeah? The option is for this to be the reduction, and if copper 2 plus is reduced to copper, then the oxidation would have to be this one going the other way, the NO2 going to H plus and NO3 minus. Right? You can't have that plus that because they're both reductions. Then it would be a red-red reaction, not a redox reaction. Yeah? And you can't have that and that because that would be an ox-ox reaction, and we don't have ox-ox reactions. You see what I'm saying? So these are our two options. What these numbers tell you is this. Because the number for the nitric acid is the biggest one, we say that the nitric acid is the better oxidant. Right? And you will see that written down everywhere. And I've never been completely convinced that that actually makes sense to say that, because you say, well, that's only, well, what's the other oxidant that it's better than? What these numbers are really able to tell you is which one of these two reactions happens. And what it's telling you is that if these are the two options, the one that will actually happen will be the one where the thing with the biggest value for the reduction potential is actually the reduction. Does that make sense? So when you look at a pair of reduction potentials like this, what I'm going to suggest, and this is kind of new this year, this might be rubbish, we shall see, you might be even more confused, is that you can think about there being two potential reactions, where the first one's the reduction, and so the second one must be the oxidation, or where the first one's the oxidation and the second one is the reduction. And what I'm saying is that the reaction that actually happens will be the one where the reduction is for the redox couple with the more positive number. Right? So this means that if you mix nitric acid and copper, you would expect there to be a reaction. If you mix copper 2 plus and bubble NO2 gas through it, you would expect there to be no reaction. Hello?
When the equation balanced to the rate, do the ratios make a difference?
No. No. It's a good point. This volts thing is not volts per mole. Right? So it's kind of different to like enthalpy, where it's kilojoules per mole. These volt numbers are independent of the amounts of stuff that are in your reaction. We'll come back to that. If I remember, we'll come back to that after the break when we're talking about the cells. Right? Okay, let's press on. So this is now kind of saying what I just said. See, this is why I said I hate this lecture. Because it's this bit which I still haven't quite found a really good way of explaining. And even though you do this at school, I know for a fact that most of your teachers don't know how to explain this either. They just tell you stuff, you absorb it like a sponge and regurgitate it, and it's all sweet. But to actually explain it so it makes sense, at least for me, is really hard. Maybe it's just because I'm rubbish, I don't know. So here's the numbers again. By comparison, if we mixed copper 2 plus aqueous and NO2 gas, we would not expect the copper 2 plus to be able to take electrons off the NO2 because it's not a strong enough oxidant. See, to my mind, that argument doesn't work. There's a flaw in that somewhere. But nonetheless. So what we can say is that because we've got reduction potential values for both of those redox couples, we can say that copper 2 plus wants to get electrons and turn into copper. And there's a number that quantifies how much that is. And the H plus and NO3 minus wants to get electrons from somewhere and turn into NO2 gas. And there's another number that quantifies how much it wants to do that. But the numbers tell us that the H plus and the NO3 minus want to get electrons more than the copper 2 plus does. So it's the better oxidant. And so it's the thing that will get electrons when you do the chemical reaction. Have we got that? Yeah.
What do you call that pair of H plus and NO3 minus? Does it
I would call that the oxidant solution. I think you have to have both, because just NO3 by itself won't do anything. It has to have the H plus as well. So it's a bit like permanganate. If you were to write the permanganate redox couple, I would write that as MnO4 minus and H plus line Mn2 plus, because you've got to have the acid, otherwise it won't work. Yeah. Okay, so then the next slide is just telling us that the E standard values tell us that the favoured reaction will be that which is the reduction and that which is the oxidation, and then you add them together, and we've done all this. I think this is here again because at one stage, the first time through on this was like yesterday. So this is all on a previous slide that you've got, right? So we won't dwell on it because you've already got it. Okay, another example. What I'm going to try and do now, before you all collapse into a coffee, is just rather than second guess myself, just tell you how I want you to think through a problem like this, right? So here we go. Can we predict what the favoured reaction will be given the following data? So here's a pair of redox couples. We've got E standard for Br minus and Br2. Sorry, Br2 and Br minus. Of course it is, sorry. Br2 and Br minus is plus 1.07 volts. And we've got E standard for I2 and I minus is plus 0.53 volts. So we would give you a pair of redox couples like this, and we would say, what is the we might even say, what is the spontaneous reaction, whatever that means. But what reaction will happen, right? And then you go, well, what's the reactants in the products? And that's the wrong question to ask here, right? You want to look at the numbers and say what the favoured reaction is. And so what we do is this. Well, we need to recognise, first of all, that that number refers to this reaction, Br2 gaining 2 electrons to make 2 lots of Br minus. And the second one refers to I2 gaining 2 electrons to make 2 lots of I minus. They're both reductions, as they should be, because these numbers refer to reduction potentials. And then we do this, right? And even if you don't really understand it, you can do this. You can say, the numbers tell us that the bromine is a stronger oxidant than the iodine because it has the bigger number. Therefore, we expect that in the favoured reaction, the bromine, the Br2, will be reduced and will take electrons off the iodide, the I minus, in the other redox couple. And so we look at the numbers, we recognise that the one for bromine is the biggest number, therefore the reduction half equation in the favoured reaction will be the one for the bromine. The bromine will gain the electrons and turn into bromide. And we can just write that down because we know that that's true, because the number for the bromine is the more positive one. If that's the case, then the oxidation must involve the iodine, but the oxidation will be iodide, I minus, going to iodine, I2, plus 2 electrons. So iodide loses electrons to make iodine, so it's an oxidation. And then we can add those together to get the overall equation for the favoured reaction. Right? And that's it. Please note that at no point on that slide have we taken reduction potentials and subtracted one from another to get a positive number to prove that that's the favoured reaction. Yeah? We're going to come to that after the break, but you do not have to do that if this is the sort of question we're asking you. All we want you to do is look at the numbers, say this is the more positive one, therefore this will be the reduction, therefore the other one has to be the oxidation, and then you just write down the equations and add them up. Right?